Identifying true developmental milestones in the adolescent brain requires researchers to bypass a significant analytical hurdle, the extreme anatomical variability found between individuals. In an MRI, a standard 1 cubic millimeter voxel captures millions of individual neurons and up to 1 trillion synaptic connections. This cellular density creates massive macro-level volumetric overlap across the population, making static snapshots ineffective for establishing diagnostic baselines. This scatter plot of total brain volume illustrates the scale of that distribution. If we isolate the data points specifically for 10-year-old boys, we find that 2 healthy subjects of the same age can exhibit a nearly 2-fold difference in total cerebral volume. Because of this overlap, gross structural volume fails to establish a reliable baseline for cognitive capacity or psychopathology. Non-ionizing magnetic resonance imaging provided the methodological breakthrough needed to solve this problem. The absence of ionizing radiation allows for safe, high-frequency longitudinal scanning, tracking the same subject over multiple decades. Reliable biological markers of cognition, the endophenotypes, emerge from the rate, shape, and timing of developmental trajectories. Total cerebral volume follows an inverted U trajectory, reaching 95% of peak size by age 6. Peaks are sexually dimorphic, 10.5 for females, 14.5 for males. Across pediatric ages, the male average is consistently 10% larger. This brain volume difference persists even when early adolescent females are taller than their male counterparts, decoupling the dimorphism from somatic growth. Gross volumetric measures do not reflect functional factors like neuronal connectivity or receptor density. Deriving functional meaning from MRI data requires dividing the total volume into specific tissue subcompartments. White matter volume increases linearly and continuously throughout childhood and adolescence. Gray matter follows a divergent inverted U trajectory, showing early growth followed by a sustained decline. These 2 tissues maintain a reciprocal relationship while following distinct maturational paths. Adolescent brain maturation is a simultaneous, decoupled process of additive transmission capacity and subtractive cellular refinement. White matter consists of the myelin sheath produced by oligodendrocytes, which wraps around neuronal axons. Myelin provides electrical insulation, allowing action potentials to leap between nodes rather than traveling the entire expanse of the axon. Restricting ion pump resets strictly to these nodes drastically increases neuronal efficiency. This mechanism generates a 100-fold increase in transmission velocity. It also creates a 30-fold acceleration in the neuron's electrochemical recovery time. Combined, myelination yields a 3,000-fold increase in the amount of information transmitted per second. This high-speed timing allows discrete neurons to form synchronized functional assemblies, a process described by Hebb's postulate that cells that fire together wire together. The continuous rise in white matter volume provides a physical record of increasing integration across distributed neural circuits. The gray matter compartment consists primarily of cell bodies, dendrites, and synaptic processes. Its inverted U-curve is driven by initial synaptic proliferation, followed by aggressive environment-driven pruning. This refinement process follows a highly specific topographical sequence across the cortex. Pruning begins earliest in the primary sensory motor areas, at the back of the brain, where gray matter volume peaks between ages 7 and 9. The maturational wave then moves toward the temporal lobes, which reach their gray matter peak between ages 10 and 11. The sequence concludes in higher-order association areas like the dorsolateral prefrontal cortex, which exhibits a late peak and a protracted decline. These sequential trajectories show high heritability, reaching levels up to 0.88. Specific modulators like androgen receptor polymorphisms shift the shape of these curves based on sex steroid exposure during puberty. The delayed refinement of the frontal regions correlates with the gradual development of judgment and impulse control. The executive control network undergoes aggressive structural reorganization well into the 3rd decade of life. Complex human behaviors emanate from the integrated connectivity of distributed networks. Subcortical structures, like the caudate nucleus, stabilize alongside or earlier than the higher-order cortical regions. The limbic system, which mediates emotional processing and reward-seeking, reaches peak sensitivity during early adolescence. This creates a critical temporal gap where reward processing systems are fully active while regulating frontal networks remain immature. Researchers measure the impact of this imbalance by contrasting cold and hot cognition. Under low arousal, hypothetical cold conditions, adolescent cognitive networks perform competently and rationally. Hot cognition involves high arousal conditions with acute peer presence and immediate real-world consequences. Under hot conditions, the still myelinating connections to the prefrontal cortex frequently fail to exert effective inhibitory control. This physiological lag manifests psychologically as temporal discounting. Temporal discounting occurs when immature frontal lobes fail to weigh future consequences against immediate rewards. This structural state facilitates a high level of neuroplasticity, as the lack of rigid myelination prevents fixed synapses from forming too early. The adolescent brain functions as a specialized plastic network, where structural instability enables rapid environmental adaptation.